So we're going to move forward with this top version of the equation, which assumes that the Prandtl number is greater than 1. And we'll just, let me turn that up. And I guess you can see what would happen if we used these other two. So here's the top version. Sort of looking at what comes next here, you have inside of this integral u infinity. Of course, u infinity isn't a function of x or y for this problem, but it could certainly be a function of x. It could change as you move along the plate, but it'll never change within the boundary layer itself. It's not a function of y, and therefore I can move u infinity out of this integration with respect to y, so I've done that here. And then also I have a ts minus t infinity, right? So that actually appears multiplying this term. And the t infinity and ts, neither one of those two parameters can be a function of y either. So I can pull that out of this integration as well. So in front of this integration now I have u infinity and ts minus t infinity, and now this is the integration that I actually need to do. And I could do this by hand without too much trouble. It's actually nice to do these integrations in Maple. So let me pull up Maple here if I can find it. So here's the Maple code that I use to do that integration. So just showing you again, I just entered the integrand. So this is 2y over delta m minus y squared over delta m squared. So I'm going to integrate 2y over delta m minus y squared over delta m squared times, and then here I have 1 minus 2y over delta t plus y squared over delta t squared. So 1 minus 2y over delta t, y squared over delta t squared. So that's my integrand. And I'm going to integrate from y equals 0 to the thermal boundary layer thickness, right? Not the momentum boundary layer thickness, the thermal boundary layer thickness, so dt. And I get this big mess, which I use the simplify command here to make it a slightly less big mess. So this is, I guess if you look at it, there's two terms here. One term is minus delta t cubed over 30 delta m squared, and then the other term is, I guess this would be delta t squared, and then 5 over 30, so that would be over 6 delta m, right? So that's what I get when I do that integration. So this integration turns into this parameter right here. If I pull a delta t out of this, you can see that all I'm left with then is the ratio of dt over dm. And since for this particular problem both boundary layers are growing together from the leading edge of the plate, I know that that ratio is going to be related approximately, at least according to the Prandtl number. So I'm going to make that simplification here. I don't have to, but I'm going to, just to make the math a little easier. So here delta m is proportional to 2 times the square root of kinematic viscosity times time, right? That's how momentum boundary layers travel. And delta t is 2 times the square root of alpha times time. So that's how thermal waves travel. And of course, if I look at this, this means that delta m over delta t is at least proportional to the Prandtl number to the 0.5. Okay. So if I make that substitution into here, then I would find that this group is delta t times, let's see, I have delta t over delta m, so that's going to be 1 over 6 times the square root of the Prandtl number, and then delta t squared over 30 delta m squared, so that'll be 1 over the square root of the Prandtl number squared, which is the Prandtl number. So this is the parameter, this group right here is equal to this integral now. So that's what I did here. I have d dx of u infinity times ts minus t infinity times this thing here, delta t, and then this group related to the Prandtl number. And on the other side, I haven't done anything. So yeah, that's where I'm at. This is my ODE that governs the boundary layer, in this case the thermal boundary layer growth. That's what I should get out of that integration process. You'll have problems where u infinity or ts minus t infinity might vary with x, in which case you can't pull them out of this derivative. In this particular problem, we can pull u infinity and ts minus t infinity out of the derivative because they're constant. So that's what I did here. I'll come back to this again, and we can think about problems where Ts isn't specified, but rather the heat flux is specified, right? So if that's the case, then this form of the equation is correct, but not super useful because I know the heat flux, but I don't know the surface temperature. But we talked about how you can go between those two things using that equation that relates the heat flux to Ts minus T infinity. But for this problem, because the surface temperature is known and the surface temperature is constant, this is a convenient form of this equation. So yeah, I pull these things out of the derivative. So everything that is not a function of x, I pull out of the derivative, which is u infinity, Ts minus T infinity. Let me find a pointer here. So Ts minus T infinity, and then this group related to the Prandtl number. And so really I'm left on this side only with d delta t dx. And on this side I haven't done anything. Ts minus T infinity cancels. I'm left here with a separable differential equation again. So I bring the delta t over to this side. So that gives me this group times delta t d delta t. That's what I have here. And then on this side, k over rho c is alpha. I have this 2. And I'll bring the u infinity down here and bring the dx here. Right? So I've separated the equation. I can now integrate both sides. So I'm going to integrate this side from the leading edge of the plate where delta t is 0 all the way to wherever I want to be on the plate surface. So that'll be at some arbitrary delta t. So I'm going to go from x equals 0 to x. And when I do these integrals, I get here I get delta t squared over 2, and over here I get 2 alpha times x over u infinity. So this is my solution then in terms of delta t as a function of x, right? Which is the next step. We're supposed to get delta t as a function of x. If I solve this equation for delta t, I get this equation here, right? So the 2's come together to make a 4. I have an alpha and an x and a u infinity. And then rather than write this over and over again, I'm just going to call it a. So a is this function of Prandtl number that we have right here. So here's how delta t changes with x. And we said that the reason why that's kind of important is because once I know the thermal boundary layer thickness, I can get any engineering quantity of interest that I want, like the heat flux. So here's the heat flux, or the heat transfer coefficient, right? The heat flux is given by, according to Newton's law of cooling, the heat transfer coefficient times Ts minus T infinity. So the heat transfer coefficient must be this quantity right here, 2K over delta T. And again, this should look pretty familiar to you because this is kind of how we understood laminar heat transfer coefficients to begin with. We said that basically getting the energy through the boundary layer is a conduction problem, right? And the resistance of that conduction resistance is related to the boundary layer thickness divided by K, where K is the thermal conductivity of the fluid. So apparently, according to the temperature distribution we're using here, the effective distance that I have to conduct through the boundary layer is delta T over 2. Right? So, but again, you get this situation where when delta T is very small, my heat transfer coefficient is very big, and then as delta T grows, I'm going to get a smaller and smaller heat transfer coefficient. So this is what I'm gonna solve for. I'll plug my solution for delta T into this equation here and get then a solution for H. So that's what I've done here. Right, 2K over delta T. So 2K, and then this is the inverse of delta T. I'd like to compare it with an exact correlation. There is a solution to this, and so that solution is given to you in terms of the Nusselt number. So let's calculate a Nusselt number. Nusselt number is the characteristic length times h divided by k. So the characteristic length for this problem is just x, which is how far am I from the leading edge of the plate. So I just substituted this h into here, and I get k over x times this thing here. The Nusselt number ought to be something that I can express in terms of Reynolds number and Prandtl number, right? That was kind of the whole point of the dimensionless analysis that we did. We showed that Nusselt numbers are functions of Reynolds numbers and Prandtl numbers, provided you're not including viscous dissipation, which we're not here, and for a specific shape, which we have here, right? So I should be able to express this in terms of Reynolds number and Prandtl number. So let's see, if I take this group here, bring the x in, that's going to put an x on top here. These k's cancel out. And yeah, so if I square the 2 and bring it in here, it cancels with the 4, and I'm left with this. And then if I want to make this into a Reynolds number and a Prandtl number, I'm just going to multiply and divide by the kinematic viscosity. And so U infinity times x over nu is Reynolds number, so that's what I have here. And then A, which is a function of Prandtl number. And then nu over alpha is the Prandtl number. So this is my expression. If I substitute in what A is, I get this expression right here. So the Nusselt number then is a function of Reynolds number and Prandtl number, right? So I can plot this as Nusselt number as a function of Reynolds number for various values of Prandtl number. And I did it for 2 values here. So here's Nusselt number as a function of Reynolds number. At some point, I can't really go any farther here because in reality, I would become turbulent at some critical Reynolds number. I can't obviously make this work or expect it to work very well for Prandtl number less than 1 for reasons that we talked about in terms of our velocity distribution. But at the 2 Prandtl numbers I picked, the integral solution, which is shown in the dashed line, agrees pretty well with the self-similar solution, which is shown by the solid line. Right? So at other Prandtl numbers higher than 1, it agrees pretty well. It starts to deviate when you really get down towards 1 and below. So it did a pretty good job, and obviously I could have done better if I would have used a higher order polynomial to represent the temperature distribution. It would have done worse if I would have used a simpler temperature distribution. One last thing I want to point out again is how flexible this technique is. So you can include all kinds of different things that are going on in the surface or in the free stream. One thing that's really pretty simple to include is the idea that if I have a problem where my boundary condition is not that the surface of the plate is a fixed temperature, but rather that the heat flux is fixed, I can use this technique to get a solution, right? So when the surface of the plate was a fixed temperature, when the surface of the plate was fixed, we had a heat flux that was varying. In fact, we could actually, use this equation here to figure out how the heat flux varied with position. Here's a different situation where the heat flux is fixed. So now the surface of the plate is unknown, right? It's going to vary with position. But the technique remains exactly the same, right? We just have to remember now that the boundary condition is different. So when we went through our derivation of the temperature distribution, that would be the same, right? When we substituted it into our integral momentum equation, that would be the same. When we did our integration, that would be the same, right? There's nothing in that was dependent on what the boundary condition was. We got to this ODE before, and the ODE remains valid. The problem with the ODE at this point, though, is that it's just not in a very useful form, because this Ts minus T infinity, before that was a constant, and so we could pull it out and cancel it on both sides. Now, if I have a constant heat flux, my plate temperature is not going to be constant, right? So I can't just pull that out. What I'd really like to have is this same equation, but written in terms of the heat flux at the surface of the plate, right? And we can go between the surface of the plate temperature, the temperature at the surface of the plate, and the heat flux, just remembering that we have this relationship between the heat flux and the plate temperature minus T infinity, right? So this was specific to our particular temperature distribution that we assumed. But if you go back and look at this table that I showed you, every one of these temperature distributions has associated with it one of these relationships between heat flux at the surface of the plate and the surface temperature minus T infinity, right? So we're using this one here, but if you would have assumed a linear temperature distribution, you'd use this one. If you had assumed a third order polynomial, you'd use this one. It's a little bit more complicated. But the point is, you have this way to go between these two things. So when I come back to here, when I come back to here, I don't want Ts minus T infinity in this equation, right? I can get rid of it and turn it into something related to heat flux. And I just do that by solving this equation for Ts minus T infinity. So now every place I have Ts minus T infinity, I can substitute in this equation here. So right here, I go to this, and right here, I go, well, I guess right here, I go to this as well. So now I have the same ODE, but it's written in terms of heat flux, which is more convenient because the surface heat flux is what I know, right? So once I have that accomplished, then let's see. For this particular problem, the heat flux is not a function of x; it's a constant. Although I could give you a problem where it is a function of x, and you would have you would have the equation at least that you could use to solve it, right? That wouldn't be a problem. Here we can bring the heat flux out and then cancel it on both sides. So that's what I did. Inside of here I have a delta T squared, right? So I'm going to have d of delta T squared. Everything else inside of here is a constant, so I can bring it out. So I brought out this a term, u infinity I brought to the other side. This 2 and k I brought over here. So here's my ODE. I'm going to separate it again, being careful this time, right? So I have a d of delta T squared, which is fine. And then I have a dx that I bring to the other side. And I have 2 k over rho c u infinity, and then I'm going to call this a again and put it right here. So we'll integrate both sides. I'm integrating an exact derivative here, so the integral of d of delta T squared is just delta T squared, and the limits are 0 to delta T squared, and over here I just get x. And I solve this for delta T, and I get this equation now for the boundary layer. It's a little bit different for the equation that I had for a boundary layer when the temperature was fixed. I mean, what you'll actually find is that when the heat flux is fixed, the boundary layer grows a little bit more slowly. It's a little thinner than it is when the temperature is fixed, right? So when the heat flux is fixed, the boundary layer is a little thinner. Your heat transfer coefficient will be a little higher, right? And that's a general observation that you'll have. The heat transfer coefficients you get under fixed heat flux conditions tend to be higher than the ones that you get under fixed temperature conditions, right? We can compare those two results. So here is my solution. I just substituted it back into this equation for the heat transfer coefficient, and I got this, which if you bring the 2 and the k inside of here, you get this equation. If I were to go back and find the equation that I got for constant temperature, you'll see they look almost the same, except for there's a square root of 2. So the constant heat flux condition gives me a heat transfer coefficient that's like 40% higher than I would have gotten for a constant temperature condition. And again, I think it's hopefully pretty obvious what the power of this is in terms of being able to deal with more arbitrary boundary conditions, more arbitrary things in your problem.